Thanks for the introduction. I'd like to thank the organizers for allowing me to talk. Okay, so a lot of this will be joint with Michael, and it was helpful. He came with his obstruction bundle gluing and intersection theory from ECH, so he was kind enough to lend them to contact homology. All right, so we're going to start off with a contact manifold. For most of the talk, it'll be three-dimensional, but in some parts, I might get to tell you about what we can do in higher dimensions. This is going to be non-degenerate contact, and it's going to be co-oriented, meaning that there's a global one form that defines the contact structure, and for grading reasons, let's pretend or assume that the first Chern class of the contact distribution vanishes, and then R is going to be my Rabe vector field. Okay, and then I'm going to have J is an almost complex structure on R cross M. And I'll take d e to the tau lambda. So here tau is going to be my coordinate on R. It's going to be translation invariant. So I have d tau. R is going, j dd tau is going to be equal to R. And I want j restricted to, I'll just say j is d e to the tau lambda compatible. Okay, then we want to count cylindrical curves. So Chris defined asymptotically cylindrical curves. Our curves, the domain is just going to be a cylinder, so it's not going to be super exciting, but they're still fun to look at. So I'll denote the space of, so let's see, let gamma plus gamma minus be periodic Rabe orbits. Mj gamma plus gamma minus is going to be the set of J holomorphic curves from a cylinder R cross S1 J0 into the symplectization. Equipped with this d lambda R invariant almost complex structure. And then we want du of j to be j of du, so we want them to be pseudo-holomorphic, and then we want the limit, so if we take r to have the t coordinate, s1 to have the s coordinate, we want the limit as s goes to plus or minus infinity of the projection of u on the contact manifold component to be a reparametrization of the Rabe orbit at gamma plus if we go to positive infinity, and gamma minus if we go to minus infinity. Oops. And then we want the limit as s goes to plus or minus infinity of the projection to the r component of u to be plus or minus infinity. So you want to think like, if my contact manifold was something stupid like a circle, then you're counting curves like this, gamma plus, gamma minus. And then there's also going to be an R action that technically you have to mod out by, coming from translations on the target. And so when we go to look at the differential, there will be this translation action, but a lot of times I'll ignore it when it comes to talking about index calculations and stuff. Okay, so,
Does anything other than the grading depend on your assumption that C1 equals 0?
No.
So I can just drop that and be happy with the Z2 grading?
Yeah, I mean, eventually I have to, yeah, so you can drop that and use the Z2 grading. Of course, when I define a dynamically convex contact form, you'll need some sort of way of making sense of the grading on contractible orbits. Okay. So the grading is given by the Conley-Zander index. On our chain complex, we have that the virtual dimension of this moduli space is given by gamma plus minus the grading of gamma minus. And here, the grading is an SFT grading. So this is going to be CZ of gamma plus n minus 3. So if the dimension of our contact manifold is 3, then you get this is just CZ of gamma minus 1. Okay. So then I can tell you what the chain complex is. So this is going to be generated by only good Rabe orbits. So we take the set of all Rabe orbits, and then we throw out bad Rabe orbits because they're bad. And so to define a bad Rabe orbit, it's a little bit annoying, but so the CZ index of a Rabe orbit can either have the same parity under iteration of your orbit or it can flip-flop between being even and odd. Sorry, odd and even. If it flip-flops, then you throw out the even multiple covers. So bad Rabe orbits even covers of flippy CZ guys. Okay, and if you want the real definition, or you want an example, so in dimension 3, bad Rabe orbits are even multiple covers of negative hyperbolic guys. Meaning that they have the eigenvalue of the linearized return map if we restrict it to the contact distribution is negative and real. Okay.
Is there a reason for your V there?
For which?
CCVQ, like in your top line?
Is there a
it's a star. Oh, sorry.
Yeah, it's not a V.
It's not a V. This is it's the vector space generated by all the Rabe orbits, and you throw out all the bad Rabe orbits.
Yeah, sorry.
He just thinks the star is a V.
Never mind. It's been cleared up.
Hey Joe. Is there another way, or why are bad Rabe orbits bad?
So if you keep them in the chain complex, even if you had all the transversality in the world, you'd never be able to prove invariance. But secretly, you can't orient curves that limit on bad Rabe orbits unless you have some sort of a parametrization you're using of your bad Rabe orbit. And so there's when you try to assign orientations, you can get both positive and negative orientations assigned to the same cylinder, and this causes a headache. And in orbifold Morse theory, you can kind of think of the bad Rabe orbits as being like the bad points whose like gradient flow lines get reversed underneath whatever action you're modding out by. Yeah. Any other questions?
This moduli space is after more parameterization of the cylinder, right?
Oh, yeah, so that is kind of incorporated by the fact that this is the projection onto the contact manifold is a reparametrization of gamma plus minus. So that already includes that. Okay. And then the differential. So there's actually two equivalent ways over Q of defining the contact differential. So either we can define it so let me just write this down and then I'll say. Okay, so either you can define it by looking at the multiplicity of the top Rabe orbit, or you can define it by encoding the multiplicity of the bottom Rabe orbit. And this epsilon u is just supposed to be some choice of coherent orientations. M of u is the degree of the covering map of the curve if your curve u is not somewhere injective. And the multiplicity of your Rabe orbit just means you've had to iterate some simple orbit some number of times, and the multiplicity will be the number of times you've iterated a simple Rabe orbit to get to x. And so it might look like these coefficients are defined are not integral, but they are in fact integral. And so you can see that because if you have a k to 1 fold cover, where you have x is gamma, let's say, plus to the kp, and y is gamma minus to the kp, this would be a k to 1 fold cover of a cylinder. Gamma plus to the p, gamma minus to the q, and so the multiplicity of x is kp, the multiplicity of y is kp, the multiplicity of this curve u is k, and k obviously divides both kp and kq. Okay. All right. So I'll just write, I guess, that m of x equals 1 if x is a simple Rabe orbit. So maybe simple hasn't been defined, but that just means that the map x, which is R mod tz into your contact manifold is injective. And m of u equals 1 if u is somewhere injective. So that looks like beautiful theory, but is not really so beautiful. So some of the issues that are going to arise is that we're working with multiple covers. Is there a question?
So, can you explain the difference between, again, these two?
Well, one encodes the multiplicity of the top Rabe orbit, one encodes the multiplicity of the bottom Rabe orbit of your cylinder. And it turns out that they're equivalent, sort of. If you had all the transversality in the world, that would mean that your differentials were defined and you actually got a homology. And then on the chain level, you could just divide and multiply out by multiplicity of Rabe orbits to pass from one chain complex to the other chain complex.
So homologies are isomorphic under this.
If you live in magical transversality.
So basically you have two different differentials.
Yes, but they're equivalent. Well. Okay, so why is this theory possibly not so correct? Okay, so the first issue is that we're working with multiply covered curves, and Chris spent many lectures telling us, as well as Dusa and others, telling us about the horrors of multiply covered curves. And then also, I think Michael mentioned this a few times, but you can look at multiply covered curves, and they can end up having negative index, even though they live in, even though they have to be there, and you can't just use a generic perturbation of J to get rid of them. And so this means that like compactness issues are going to suck. Well, maybe they don't suck. Maybe they're beautiful, but they make the theory harder. All right, so everyone's favorite congerum from 2000, which was in a paper by Alyashberg, Gimental, and Hofer, says that assume there are no contractible Rabe orbits of index -1, 0, or 1. So this is this grading. That's the Conley-Zander index plus n minus 3. And, well, okay. It also started by saying let Y C be a non-degenerate contact manifold. Then the differential is well defined. Of course, no one really said which differential they were using, which adds another layer of confusion, but that's okay. Oops, and J is generic. Okay, that you actually get a homology, so dq squared is 0, and this homology, which depended on your contact form, your choice of J, was actually an invariant of the contact distribution, so e.g. independent of the choice of lambda and almost complex structure J.
But I think to be fair, they didn't quite say that because they said that some abstract perturbations of the moduli spaces would be needed, but they wouldn't go into the details of that in that paper.
Because this one is demonstrably false.
Okay, well, this is, well, it doesn't even appear in this form in their paper. It appears as a series of like lemmas or propositions.
I mean, they said at the beginning, this is all assuming some
Okay.
perturbations have been made.
Well, at the beginning it said that this is all like conjectural, blah, blah, blah. So this is why it's a congerum. So it's a conjecture, okay, plus.
So the conjecture is that this statement can be corrected.
Yes. Well, the other problem is that some people then said you don't need abstract perturbations and this works anyways. Okay. Is anyone happy? No? No one's happy? Okay. Okay. So, what is this beautiful compactness that I alluded to? So this is Bourgeois, Alyashberg, Hofer, Vysotsky, and Zander. This is a result from 2003. Again, I'll paraphrase this result. So there's no bubbling like in Hamiltonian Floer theory, but we do have breaking of curves into buildings. So Michael drew some beautiful buildings of asymptotically cylindrical pseudo-holomorphic curves. And so the heuristic reason for why we have this breaking is because so there is a maximum principle in the R component of the symplectization, but you can grow minimums, and so if you try to compactify the space, you're going to be allowed to develop new punctures at the bottom end. So you had some index 2 cylinder, you could conceivably start to have, this is the picture people draw, so you have some sort of a minimum developing in the R direction, and so then if you want to compactify the space, you could pop off a plane, and this would be a allowable element of your compactification if you could not sort of exclude it for other reasons. And then this makes us sad. broken cylinders in your compactified moduli space of index 2 curves.
I have a dumb question. Why do you call this breaking and not bubbling?
How much?
Because you have a cylindrical end, which is has a real glowing parameter instead of a complex glowing parameter. I mean, it breaks like a trajectory in Morse theory or floor theory, and not like a bubble in chroma living.
Okay, that glowing parameter is
So I'm not going to draw a complicated sequence of buildings, but you can imagine that sort of, well, Michael was talking about how you can have branched covers of trivial cylinders. Those guys can, have index 0. So you could be in some situation where x is gamma squared, z is gamma, and then the cylinder could break to be gamma squared, gamma, 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 and this could be a holomorphic plane of index 2. This guy has index 0 and this guy has index 0. So this would be an allowable compactification. And in dimension 3, there's really nice iteration formulas for the Conley-Zander index plus automatic transversality, so I'll explain in a minute how you can salvage this theory in dimension 3. But in higher dimensions, you can have cylinders of index 1 and you take their multiple cover and they suddenly have negative index. And then that means that you, in other elements of your compactified moduli space, are going to have to include things like a chain of cylinders where you just have to end up being able to add to 2 at the end of the day. So that makes things complicated. And the philosophy with a lot of this stuff is, well, if we only had some more injective curves, you just pick J generically. So all of my moduli spaces have to have positive virtual dimension because we're working in a symplectization and have this R action, and the only way that you can add to 2 with positive numbers is 1 plus 1. And this original assumption about no contractible orbits of index minus 1, 0, 1 come because this sort of building is not excluded by the assumptions, but you could have some building where you have 1, 1, and 1. So this is like why the assumptions in the congerum exist. And then the 0 and minus 1 sort of come up when you try to prove invariance and homotopy depending on what level of transversality you want to assume. Okay, so let me see. Okay, so it turns out that in dimension 3 you can get automatic transversality and index calculations to work favorably. And so in my thesis, I found not a very large class of contact forms, but a class of some contact forms where you could actually define contact homology. Sort of the definition I came up with is we say a contact form is dynamically separated provided the Conley-Zander index of gamma is between 3 and 5 for gamma simple and contractible. And every time you iterate gamma, you're just increasing the Conley-Zander index by 4. So this holds, and then plus you can do this if you, so I guess I should say, if gamma is non-contractible, have analogous definition, but you have to keep track of free homotopy classes of Rabe orbits, and it just becomes a mess to write down, so I'm not going to. Is there a question in the front? Okay. And then the theorem that I proved is that if on this condition, this is usually true up to large action. And action is the integral along gamma of some Rabe orbit. So by up to large action, I mean for all Rabe orbits of action less than or equal to something, you have this dynamically separated property, and these guys all, for the most part, arise as there's a natural class of perturbations you can put on prequantization spaces, so this is where these guys come from. So if y3 lambda is non-degenerate dynamically separated, then, and J generic, then the cylindrical contact homology is defined, and sometimes up to like some large action index, sort of. So if you don't have this dynamically separated for all of your Rabe orbits, but only up to some large action, then you can only define cylindrical contact homology up to that large action and index, and then there's a way you can take direct limits to actually sort of compute it. Invariant under the choice of J, and dynamically separated contact form. Okay, so this is not so awesome because it excludes a lot of examples, like dynamically, like certain dynamically convex things like ellipsoids. So you team up with someone that knows more than you, and then you prove a theorem. Hook thing is annoying. Okay. Okay, so a dynamically convex contact manifold is something that Hofer, Vysotsky, and Zander studied in the 90s. And what Cochrane knew as HWZ papers when she was a graduate student. A dynamically, so y3 lambda is dynamically convex, provided the first Chern class of the contact distribution restricted to pi2 of y is 0, and the Conley-Zander index of gamma is greater than or equal to 3 for all contractible Rabe orbits. Okay, and so an example is any strictly convex hypersurface in R4 with a standard symplectic structure, which is transverse to the radial vector field. Okay. So this is a nice class of contact manifolds because I erased the theorem, but it's basically without sort of a theory of abstract perturbations, it's going to be the class of contact manifolds so that all the contractible Rabe orbits give rise to planes that all have to have virtual dimension at least 2. So this would be sort of like a nice class of manifolds you'd like to prove contact homology is defined for an invariant in dimension 3. Okay, so,
You can also drop the assumption in C1 if there are no contractions.
oh yes, okay. Or no contractible orbits. So we'll make condition A, C1 of pi 2 is 0, or B, this thing. Okay. So what Michael and I proved is that if y lambda is dynamically convex, J is generic, then the only buildings of index 2 in R cross M are either just a cylinder a once broken cylinder or if you, okay, I should also write this. So we're going to assume that Conley-Zander index of gamma is strictly greater than 3 for gamma non-simple and contractible. And I'll explain why in just a second. Or you have a pair of pants, a plane, and a trivial cylinder. So gamma squared, gamma, gamma, gamma. Okay. So this is 0, 0, 2. Okay. So we have this extra assumption that this should be gamma d, d minus 1. Okay, sorry. Okay, so we have this assumption that the Conley-Zander index is strictly greater than 3 for gamma non-simple and contractible. We expect that it's removable, but we have to do a little bit more estimating things to make sure that something bad doesn't happen in the next blackboard. But sort of what we proved is that the only buildings of index 2 are either an unbroken cylinder, once broken cylinder, or this pair of pants configuration. If you don't have this assumption, then your pair of pants configuration can have like this gamma could be gamma to the d1, this could be gamma to the d2, and then this is just a d1 plus d2 fold cover of a trivial cylinder. And the second part of our lemma is that no index 2 cylinder can limit to the third configuration. So we didn't prove that there are no buildings of this type. There certainly are. But we just showed that there's no index 2 cylinder that could limit to it, which means that as a corollary, the cylindrical contact homology differential is well defined and it squares to 0. And this is in a symplectization. So the reason why we don't have invariance yet is because this sort of analogous lemma in cobordisms for sure does not hold. Okay. Any questions?
So a priori, what are the possible configurations for that third one? I mean, like what? I mean, I'm looking at this and you're saying if it can't be the case that a cylinder, if it can't be the case that a cylinder of index 2 limits on the third configuration, I'm looking at that thinking, okay, well, if in some world I could perturb and actually glue that thing together in some sense, then it would be an index 2 cylinder. So therefore,
But if you like, what kind of perturbing do you want to do?
well, that's sort of my point, right?
So
that means that
if you were doing obstruction bundle gluing and you decided to try to see if you could do this, the number of ways you could glue it together would be 0.
Actually, just to That's not how you prove it, right?
No. It's a proof by contradiction. Sorry. So we use.
It's kind of intersection theory.
Yeah, you use intersection theory. You say, like, suppose you have this curve limiting to this, then you look at some intersection theory properties and prove that you get a contradiction. Therefore, your index 2 cylinder can't limit to a building of that type.
The true proofs are actually the same if you look deeply enough.
Yeah, and since obstruction bundle gluing goes back to winding numbers and
Actually, well, can't the obstruction bundle gluing, can it only tell you that the sign count of ways to glue is 0, whereas this is really telling you there's no way to glue? Or
I think in this case you'll actually see if the obstruction section never vanishes. So that's it.
And where do you use in the proof that the form is dynamically convex?
Sorry?
I know that the proof has this intersection theory stuff, but
Oh, the intersection theory stuff is to prove that no index 2 cylinder can limit to the third configuration.
and where is that do you use the fact that it's dynamically convex?
Oh, so we use the fact that it's dynamically convex to prove that the only buildings of index 2 are of those 3 types. And then you also, yeah. And then you're also using automatic transversality and some index stuff, and proving that those are the only 3 types of buildings, and that's also what's getting you the transversality you need to say that the differential is well defined. So we also prove that all index 1 and index 2 cylinders and sublectizations are cut out transversely, and
But do you need dynamically convex for that?
so you don't need dynamically convex for that, but you're going to have a problem with looking at your compactified moduli space of index 2 cylinders. Like, then I'm going to have way more things, and I'm not going to be able to prove that d squared is 0.
Let's say you know that you only have these 3 kinds.
You can only get that if you're dynamically convex.
We all have bad vision, the old people in the front. But what are the indices of the curves in the third building? It's 0, 0, and 2.
Yeah, I didn't want to put the zeros here and here, because then the people in the front row would ask why those curves had genus and I was counting cylinders.
Yeah, no, it's good. I just need glasses.
The top level there is a branch cover of a trivial cylinder. though.
Yeah, I should have.
Okay, that sounds good. That's fine. Okay.
And the other guys want
Okay. I got it.
He's an under.
He's a trivial cylinder. Everyone happy? If you're not happy, I'll get out my hook. I actually really like holding the hook, but I think that makes for a slightly scarier talk. Oh, yeah, and I guess, so I was going to move on to the non-equivariant part of the talk, but do people have any other questions about what goes into the lemma and corollary? I guess I should maybe upgrade it to a theorem, but okay. Anyways, okay, so 2, we're stuck on invariance, so we need to do something. So we'll try to define, we'll define stuff non-equivariant. So we'll define a non-equivariant version.
By stuck, you mean that approach.
Oh, yeah.
We're not actually stuck.
Okay. So to clarify, this normal approach looks bad because you can't prove sort of this sort of lemma in cobordisms. You also don't have the sort of automatic, you have some automatic transversality in cobordisms, but it's not good enough, and you're not going to be able to prove the chain homotopy equation, so invariance is not really going to go so well. So what we can do is we can define a non-equivariant version, And when we set up a non-equivariant version, it's kind of analogous in Hamiltonian Floer theory to when you pick a time-dependent Hamiltonian. So all of your curves end up being somewhere injective. So we're going to do something similar in the contact world. There's still going to be some things we have to work out, but they're doable. And then it turns out that there's a way to take an S1 equivariant version of this non-equivariant picture, prove that it's isomorphic to the classical cylindrical contact homology, and in a very roundabout way, get invariance for the classical cylindrical contact homology. Okay, so this non-equivariant theory is kind of look like the positive part of symplectic homology, whereas this cylindrical theory, if it was defined, it would look like the S1 equivariant version of the positive part of symplectic homology. But we don't want to use symplectic homology because we'd like to define something directly in terms of the Rabe data and in terms of asymptotically cylindrical pseudo-holomorphic curves as opposed to looking at the Floer equation. Okay, so we're going to take J here, instead of using 1J sort of for all time, we're going to take a domain-dependent J. So JT for T in S1 is going to be an almost complex structure. We still want for each time T that it goes to the Rabe vector field, and we want for each time T that it's d e to the tau lambda compatible. And then we're going to be counting, well, we're not going to be quite counting pseudo-holomorphic curves where I just throw this T dependence in, because that's not going to, automatically get us a non-equivariant version. We're going to have to be a little bit more careful than that. But the moduli space we're going to start to want to look at and put point constraints on is going to be this guy where we're using a domain-dependent family of almost complex structures. Okay, so you just put a T in your J holomorphic curve equation. Okay, and this T depends, oh shit. Wait. Sorry, my R coordinate should have been S and my S1 coordinate should have been T. Now it makes a lot more sense. Okay.
Then maybe this is stupid, but what happens when if you make lambda time dependent?
Well, so this is forcing, in some sense, you can't make your lambda time dependent. This is like the closest you can get to forcing your periodic orbits to be time dependent.
I can't make lambda time dependent?
It's a contact, like how would you make it time dependent? It's just a contact form.
But you could take a loop of contact forms, given the same context form.
But I would rather take a loop of...
We're not looking at period 1 orbits, we're looking at arbitrary period orbits.
Oh yeah, that's the other thing. Sorry. I mean, the point is now all the curves that were multiply covered are no longer going to be multiply covered for a generic family of almost complex structures that depends on the domain. So the good news for a generic family, M, J, gamma plus, gamma minus is a manifold of dimension equal to the Conley-Zander index of gamma plus minus the Conley-Zander index of gamma minus. And I broke some symmetry, so it's got an extra dimension on it. All right. And so you're going to be working in a situation where so there's a paper by Floer, Hofer, and Zalman that gives you transversality in the Hamiltonian Floer case. And so this is sort of you can't pick a time-dependent Hamiltonian, but you can pick a time-dependent almost complex structure in your J holomorphic curve equation. And so that's how. So all your curves are going to be somewhere injective and ta-da. Okay, but you're not going to be able to define the differential sort of in this naive way here. So let me tell you how to define the differential. Okay, so to define a differential, we're going to need to throw in some point constraints. And this is kind of how we're forcing a parametrization of our Rabe orbits in terms of time. So, okay, so here's my curve. I'm going to be able to look at u of r cross 0, and this is going to pick out some line on my cylinder. Okay, and you can use this to define evaluation maps from our moduli space into the image of gamma plus minus, which we define to be the limit as s goes to plus or minus infinity of the projection of the curve when we look at time 0. Okay, so this is supposed to be like when t equals 0. And this is some point that's in my Rabe orbit gamma plus. And you can, do the usual thing where you can map this evaluation map descends to an evaluation map after you quotient out by r, because even if we do define a differential, we're still going to have to mod out by r, where this r is coming from the translation in the symplectization direction. And what do I want to say? Okay, and then my chain complex, I no longer have to throw out all these bad Rabe orbits, but I am going to have twice the number of Rabe orbits in it as before. So you can kind of think of this as a Morse bot version, where your Morse bot manifolds are your Rabe orbits, and you put a height function on S1, and so that gives you two critical points, and one critical point has index 0, one has index 1. So we're just going to kind of, that's not really what we're doing, but it's the vestigial motivation for defining our non-equivariant chain complex to be generated, so it has two generators associated to each Rabe orbit. So gamma check and gamma hat. Gamma is any Rabe orbit. And then I'm just going to arbitrarily shift the grading up on my gamma hats by 1. So we have that gamma, the image of gamma, okay, I'm just going to say that gamma Conley-Zander index of gamma check is equal to gamma. Conley-Zander index of gamma hat is equal to the grading. Oh, I've reversed this. So I should have written the inequalities the other way, but the grading on gamma, oh my god, what am I doing? Okay, I'm getting confused with hats and checks. Okay, so the grading of gamma hat is going to be equal to the Conley-Zander, the grading of gamma check is going to be equal to the Conley-Zander index. The grading of gamma hat is just going to be the Conley-Zander index shifted up by 1, and Conley-Zander index of gamma hat and gamma check doesn't make sense because it's the same underlying Rabe orbit gamma. So this should be the correct formula. So you should just think that I have gamma check and gamma hat are formal variables associated to the Rabe orbit gamma. Okay. Yeah, this is any Rabe orbits. You allow also the bad Rabe orbits. So it's just like in symplectic homology, you would also see the bad Rabe orbits. Okay, and this is kind of, so this, what do I want to say? This non-equivariant picture is sort of not original, but it is an adaptation from stuff by Bourgeois, Liashberg, and Ekholm, and also Bourgeois and Wancha. Okay. All right. And now my differential is going have a block decomposition. And I'm going to have sort of stuff that goes from check Rabe orbits to check Rabe orbits. So there's 4 different ways sort of you can go from, let me just write this out and then we can talk about it. So hat, this is just Z generated by this guy, and CC check equals C. Okay. So, all right. All right, and I promise that you'll see this evaluation map that I just wrote down show up.
Should we think of it as like a triumph that you no longer have to throw out the bad Rabe orbits? Like, is that something desired, or is it just a quirk of this?
I mean, so it is desirable, and it turns out that this S1 equivariant version, like once we figure out what the S1 equivariant version of this non-equivariant theory is, it's actually defined over Z. And so it's going to have more information coming from bad Rabe orbits because it's defined over Z. And it turns out that if you tensor that theory with Q, you get the usual cylindrical contact homology theory. So it's a quirk, but I guess it's good because you get more information. Okay, so what do each of these terms count? So D check, alpha check, beta check. So here you would want the degree and index between alpha and beta to be 1. So this will count cylinders where you are going to, right, so you're going to fix a point on the underlying simple Rabe orbit associated to alpha. So this is some point on the image of, and alpha bar is a simple Rabe orbit. To alpha, and then we want, so this is going to be curves U in this moduli space going from alpha to beta mod R with the positive evaluation map of your curve U being equal to P alpha bar. And we're also going to have to count Morse bot buildings with a cyclic ordering condition. So the evaluation map constraint is supposed to be this sort of point where P alpha bar, it needs to match up with pi y of U of S0. And then we'll count these guys, and then we'll also have some buildings that we have to count where you've got a cyclic ordering condition, meaning that you want ev minus of the top curve, ev plus of the bottom curve, and whatever point you're picking on this intermediate curve, let's call this guy gamma, to be ordered this way as you go around gamma. So you're going to need to orient your, like a direction for how you're going around your Rabe orbit. Okay. And then D check of alpha check, beta check is going to be something analogous, except instead of having the positive evaluation constraint, you're going to have the negative evaluation constraint. And then negative constraint. D plus alpha check beta hat. This has no constraint. So this looks like the too bad map that you see in the Bourgeois-Liashberg-Ekholm formulation. So if we look at D plus of alpha check alpha hat alpha check, you get 2 points if alpha is bad and 0 if alpha is good. And D minus alpha check alpha hat, this has constraints at the top and bottom. And this non-equivariant theory is not really so easy to count because not only are you sort of counting cylinders that either have 1 point constraint, 2 point constraints, or 0 point constraints, you also need to count more spot buildings that have the cyclic ordering condition. And these more spot buildings, they're not going to be of infinite length because you only have a finite number of Reeb orbits in each Conley-Zander index, but you know they are going to be some sequence of buildings that you have to figure out how to count. But it turns out that so a theorem is that this D minus here. So this also, in addition to counting U and M alpha beta with EV plus and EV minus constraints and more spot buildings, it also will count ways to glue an index 3 curve using obstruction bundle gluing that looks like a branch cover of a cylinder. This is 0, 2, and 1. Okay.
What is the J on the cap there?
It's a 2.
No, it's a J. I mean, so you fix a family J of T on the domains.
Yeah.
So what would that be on the cap?
It's constant.
So it's a bubbling off at a point, basically. So
Yeah.
it's constant.
Yeah.
So some J where it bubbled off.
Yeah.
Is it clear why you can only have one plane that bubbles off?
Yeah, index calculations.
Is the reason that you define this chain complex over Z that the high independence means you can rule out isotropy?
Yeah. So your curves are always going to be somewhere injective. So you don't have the isotropy anymore to deal with. Okay. Right. So for Y3 lambda dynamically convex, or Y2n minus 1 lambda, well, no, I don't want to say that. This non-equivariant contact homology and J generic is a chain complex, and the homology of it is independent. This is a family of J's. Of your choice of family of J's, and the dynamically convex lambda. And let me tell you how to relate this back to cylindrical contact homology in a way that will make everyone much happier than they are now. And then I will be done. Okay. So if there is sufficient automatic transversality, then as needed to define the classical cylindrical contact homology differential, then we can use, for some generic choice of J, we can use this J to, I don't know, look at this non-equivariant contact homology. Okay. And what's nice is that it turns out, so in this case, D check looks like the standard cylindrical contact homology differential, and D hat looks like the other cylindrical contact homology differential, and you end up having opposite orientation, but that's not so important. But it turns out that you can show that, so if y lambda is non-degenerate, dynamically convex, J generic, then for D0 equal to dq minus d, well, I did not use good notation for this. So the first differential, this is supposed to be the second differential that I told you, d plus, d minus, and d1 equal to 0, 0, multiplicity of gamma 0. I'll explain what that is in just a sec. You can actually get a chain complex by taking the non-equivariant chain complex, tensoring it with a formal power series, a variable 2 that has degree 2. So here U is a formal variable of degree 2 with dz being equal to d0 plus d1 and this j, that this is a chain complex, and
With U inverse J, D1.
sorry?
You have to multiply D1 by U inverse.
Oh yeah, sorry.
So then your differentials there, they never saw bad orbits before, so they ignore them in the second one.
So these
Because
ones,
you said in the second complex there was a different orbit.
so this was kind of a lie. So you still will be able to see your bad orbits, and you're not going to have the problems that you had before with orienting them, because you have point constraints running around that are going to allow you to deal with orientations. So I'm doing a bad job explaining this because there are a lot of details I'm omitting.
No, but then, so the degrees of D0 are coming from a complex where the bad orbits.
Oh, okay. This shouldn't be. I should have just written. This isn't technically this differential. It should be. I should have written something like this is counting. Oh God. My notation is really awful. Yeah, we'll just use d hat and d check, and but they have a more familiar expression in terms of multiplicities of ray orbits and multiplicities of your pseudo-holomorphic curve. So what I should have written here is that if J is, if we can replace J with a single J, then D check counts U and M, J, alpha, beta. You still are going to have your checks and hats with a point constraint at the top. And you'll get that D check of alpha check is going to be the sum over the multiplicity of alpha divided by the multiplicity of your curve U that connects them. And now my font has become microscopic. Beta with the orientation. So the chain complex is still this thing that we're using. And then the differentials just have more familiar expressions in terms of the previous differential. But that was a very unclear, unhelpful way that I explained that.
Can I just say one thing?
Yes.
I mean, the D pad and the D check, they're the same as the differentials before when you're going between good orbits.
Yeah.
And then something else when you...
Yeah.
So the answer
when
you
you're
just ignore.
Yeah, and you can show that when they do encounter bad ray orbits, nothing horrible happens.
They're sometimes non-zero between the other.
Yeah. I should finish the statement of the theorem. And the homology Z of this chain complex is independent of lambda and J, and a proposition is that CHZ tensored with Q is isomorphic to CHQ. And so this is how you end up getting invariance of cylindrical contact homology. Okay. And I will end.
Questions?
So how serious is this restriction about any complex? I know that you mentioned before in the star-shaped hypersurface and it takes 5 to 10 minutes to convert for.
Yeah.
But in general, I mean, how...
I mean, if you don't have something that's dynamically convex, then you're going to have to be working with like full SFT or symplectic homology.
But do you know any examples of complex structures which do not support constant?
Yeah, so if you take the connect sum of two tight spheres, you're no longer dynamically convex. So this sort of result doesn't work for connect sums, but I mean cylindrical contact homology was never built to be an invariant of things that weren't dynamically convex in dimension 3. And so there was a result that Viterbo mentioned in his talk where he said that if you have this assumption about Conley-Zander indices, then the positive part of symplectic homology is an invariant of the contact structure. It's exactly this dynamical convexity condition, and it has an analog in higher dimensions.
What's your favorite manifold way you can compute it?
The sphere. You can also compute it for like lens spaces and like prequantization spaces.
What's the answer?
Well, I guess I can just say it in words. For the 3-sphere, you have Q in every even dimension that's greater than or equal to 2. For lens spaces, you also only have, for Ln plus 1n, you have n copies of Q in dimension 0 and n plus 1 copies of Q in every even dimension that's greater than or equal to 2.
Any more computation requests? Other question?
Is the right way to think about why you choose this formal variable that you're doing something analogous to the draw model for equivariant homology?
Right, so that's what you're doing, but you've kind of been able to cheat a little bit. So normally your differential would have like an infinite number of terms in it, but because we could cheat and use a time-independent almost complex structure and still be able to define the complex, that's why we were able to drop the extra terms, but that's pretty much exactly what's going on.
Suppose you took two dynamically convex, just going back to the connect sum idea, if you took two dynamically convex and then you did a connect sum, but you did a really, really, really small connect sum, where you have very precise control over this sort of, you have very precise control over this hyperbolic orbit in the finite energy planes that would be sort of introduced. Is there any chance that these ideas could extend in that case?
I mean, maybe, but it's my understanding that even when you do a connect sum, you always end up introducing a new wave orbit.
But you know exactly where it is, and you know pretty clear. Yeah,
But it might generate longer ones somewhere.
Yeah, you can take multiple covers
But
of
you
it.
could use action filtration arguments anyway.
No, because so my answer is no. Okay. So, I mean, it's conceivable that we could define some sort of linearized contact homology if there's another type of building that we would have to consider, and we'd have to be able to understand how to glue it or exclude curves limiting on it, and you'd have to take some sort of like augmentation. So
I'm gonna disagree with you on this one.
you think
I think we might be able to do it.
Well, I was saying you might be able to
linearized,
without okay.
It might be possible, but it's a harder project.
Yeah. Anything is possible. Okay, I think Helmut's ready to clap for me and get coffee.
Yes.